Okay, so today we're going to look at a concept called resonance with Lewis structures. So far, all the Lewis structures we could draw, there was only one possible choice of how to do it. But what if there's more than one possible choice? The example they use here in the PowerPoint is the sulfur dioxide molecule. Let's come off to our whiteboard and do this ourselves rather than just watching them do it. So we have sulfur dioxide. So there's S in the middle, attached to an O, attached to another O. Okay, it's the plausible skeletal structure. Now, how many electrons do we have to work with? Each oxygen brings 6, that's 12. Sulfur brings 6, it's another S2P4, that's a total of 18 electrons. All right, so 2, 4, there's our bonds. 6, 8, 10, 12, 14, 16, 18 electrons. Okay, so does that work? Oxygen got an octet, 2, 4, 6, 8. Other oxygen got an octet, 2, 4, 6, 8. Sulfur has 2, 4, 6. It comes up short. It needs electrons down here, doesn't have them. So how do we fix that? Well, we already established we can remove, let's say, these 2 electrons right here and make a double bond. And that's a plausible, valid Lewis structure. But wait, couldn't we have also done it over here to this oxygen? Then we would have had this Lewis structure. 1, 2, 3, 4, 5, 6, bond, bond, bone pair, 1, 2, 3, 4, make a double bond over on this side. Okay, that oxygen ended up really ugly. So you see how on the left-hand side here, I chose to get rid of electrons from the left oxygen and make a double bond over there. On the other structure, I chose instead to get rid of electrons from this oxygen and make the double bond on the right-hand side instead. First of all, does it matter? Well, it matters to the atoms. They're both oxygen, so we can't really tell them apart. But what if they were different elements? What if one was oxygen, one was like a chlorine or something? Or even, what if we used different isotopes of oxygen? We'd be able to tell it apart. The other issue we could tell apart is, remember, double bonds are shorter than single bonds. So this molecule would have a long bond here and a short stubby bond over there. The other molecule, similar but flipped. Long bond, short stubby bond. So either way you look at it, the molecule, now it turns out this molecule is bent at an angle, which we'll learn why that's the case later. But no matter how you slice it, this molecule should, according to what we see here, look like this. And it could be flipped the other way, obviously. But it would have an asymmetry about it. No matter which of these two structures you choose, there'd be an asymmetry about the molecule. When they actually look at the structure of the molecule using X-ray scattering and things like that, they find that the actual bonds are equal to each other. So what you really have is sulfur bonded to oxygen, oops, and both bonds are the same length, not one shorter than the other, which would be implied by a double and a single. Even more intriguing is when they measure the length of these bonds, the length of the bond is roughly halfway between a single and a double bond length. So it's almost like you have a 1.5 bond here and a 1.5 bond here, which, well, how do you draw a Lewis structure of that? You really can't. What it's indicating is happening is electrons aren't dots. We're drawing them as dots and thinking of them as little particles, but remember, they're really wave functions and they're delocalized. The electron clouds are smeared out across the molecule, just like we saw back a couple chapters ago. So we're trying to show the bond forming either over here between these two atoms or forming over here between those two atoms. The reality is that double bond doesn't have to choose which side it's on, just like Schrodinger's cat. That double bond can be both places simultaneously. So the reality is you have a single bond here, a single bond there, and then you have a double bond smeared across the molecule. We call that bond delocalization, and we'll talk more about that later. the net result is you get the equivalent of 1.5 bonds on both sides. You get equivalent bonds, not asymmetric bonds. Okay, great. So how do you show that in a Lewis structure? You really can't. So what we do is a cheesy little way of kind of showing it is we show both structures that we drew, and then we draw a double-headed arrow between them. Oops, oh my god, I messed that arrow up. We draw a double-headed arrow between them. I probably should use an eraser to fix that. There. Intriguing, isn't it? That double-headed arrow between them is showing that something we call resonance. It's showing not that they're flipping back and forth, but that the two models that we could draw should be merged into one average model. They call it resonance, and you might hear things like bells resonating or vibrating, because originally they thought the molecule was literally vibrating back and forth between the two structures. It was first this, then the bond flipped, then it flipped back, and so on and so on. So they kind of thought the molecule was resonating back and forth between the two. Obviously now we know that's wrong, because otherwise it would be doing this and then flipping sides, and the bonds would be growing, shrinking, back and forth. And the reality is it's much more stable, 1.5 bonds. So we still draw it as a double arrow between the two structures. We still call it resonance, but we realize now the reality is it's not resonating, it's not vibrating, it's just simply merging the two structures. Okay, so again, if you have resonant structures, if you have two or more possible structures you can draw, we say we have resonance. We draw both or all the possible structures, and then we draw a double-headed arrow between them to indicate there's resonance. So let me come back to the PowerPoint, and they'll walk us through that a little more slowly, I guess. They're showing sulfur dioxide, and they're showing adding up to get 18 electrons. And notice they came up with the same thing we came up with, well, at least right here they did. Form your bonds, give all your lone pairs to get oxygen and octet, get the other oxygen and octet. Lone pair on sulfur, we're short an electron pair, so you form a double bond over here. And there's exactly the structure we drew, or you can draw the double bond on the other side. Again, when you have two equally valid Lewis structures like we have here, we call that resonance. Neither structure is completely accurate, but since you can't draw a 1.5 bond using Lewis structures, we draw both partway accurate structures, and then the double-headed arrow means everyone knows, mash them together. And that's your resonance average. Okay, they talk more about that. And right here they talk about how the length of the bond and the strength of the bond is between single and double, and that's kind of our experimental evidence for all this. And there's the double-headed arrow showing resonance structures. Don't forget, you can do this with polyatomic ions also, and you'll, just like before, have to account for the charge of the ion to gain or lose electrons. Let's not look further than that. I want to show you one more example, so I'm going to come back to my whiteboard here. That's what I'm calling it now. Don't need to save my artwork. Let's do carbon dioxide like we did yesterday. So we had COO, and now remember I messed this up at the time, but we have 6 and 6 is 12 plus 4 is 16 electrons, right? So 2, 4. Remember we needed to make 2 double bonds, 6, 8, 10, 12, 14, 16, and that was the Lewis structure we came up with for CO2, carbon dioxide, right? But could we have done it a different way? Well, let's come over here. Couldn't we have put 3 bonds over here and only 1 over there? Now, that means 2, 4, 6, we only need a lone pair here to get to 8. And then here we only have 2, 4, 6, 8. There's the octet. Carbon still has 2, 4, 6, 8, so it's still good. So, we have the same exact number of electrons, 2, 4, 6, 8, 10, 12, 14, 16. counting here, 2, 4, 6, 8, 10, 12, 14, 16. Same exact number of electrons, just arranged differently. Instead of 2 double bonds, we have a triple and a single. Is there another way we could do it? Sure. We could go to the other side, right? We could do the triple bond over here and a single over there, which puts 1 lone pair and 3 lone pairs. And clearly it adds up to the same number of electrons. Notice, by the way, once you draw one plausible Lewis structure, you really don't need to keep recounting all your electrons. You know you need 1, 2, 3, 4 bonds and 1, 2, 3, 4 lone pairs. So once you establish that 4 bonds, 4 lone pairs, you can easily shift them around. Shift your bonds to be instead of double-double, toil and trouble, you can make it a triple and a single, and you still need 4 lone pairs. You just shift the lone pairs around, but there's still a total of 4. And when you do it here, you just flip it to the other side. So resonance occurs here. We have our double-headed arrow. I actually drew it correctly-ish. And another double-headed arrow. I couldn't fit them all on the same level, so they're at angles to each other, but whatever. So you have resonance among all 3 of these structures. What's the actual carbon dioxide molecule like? It's an average of all 3 of them. So each bond acts as roughly a double bond. 1 plus 2 plus 3 divided by 3 gives you a 2-ish. So each counts as roughly a double bond, but this bond between each C and O is not a regular normal double bond. It's a merging of a single, a double, and a triple bond, all overlapping realities all at once. And so the bond between carbon and oxygen is simultaneously single, double, and triple. Averages out to roughly acting like a double bond. Same for the other carbon. So that's what resonance is all about. So I think it's pretty cool stuff. Today we'll just play around with drawing some resonance structures, making sure you get the hang of it. Tomorrow I want to look at a factor that will help us determine maybe among these resonance structures, maybe they're not perfectly equal to each other. Maybe some are more equal than others, for those of you who read George Orwell. So we'll find that it's not always exactly as we think it is. Sometimes resonance is perfectly equivalent, 50-50. Sometimes resonance, maybe one structure is better than the others and will contribute more to the average of the wave functions. But that's tomorrow's lesson. After tomorrow's lesson, we'll be done with the first half-ish of the chapter. So that would give us Wednesday to do a little reviewing, and then Thursday I'd like to take a quiz on this Lewis structure stuff. And so we'll go from there. All right, so I'll give you some homework on this to play around with it, and then see you tomorrow.